Go back to this. Okay, now you can see what I'm writing, I hope. I did not even pay attention to that. Oh man, it's distance education. You never know what you're gonna get. So, um, so stratified sampling, right, to reduce variability, um, separate into groups. I'll go over it again. Your sampling, the whole goal of sampling is to have a representative um, of the population. Purposely separate into groups that are different from each other. Select a random amount from each group. That's your stratified cluster. You have small clusters that are diverse. They look like mini populations. Remember, mini-me, mini populations. And then after you divide into your clusters, you randomly pick a cluster or two or three or however many you want to pick, a cluster, and sample everyone in it. Whoa, everyone. Ah, dang it. Sample everyone in it. So that's the difference between cluster and stratified. So stratified, remember, we always got these two confused. Stratified, remember, is your groups are all different from each other, like ninth grade, 10th grade, 11th grade, 12th graders, right? They're all different from each other. And then I pick a random from each one, so I get everyone represented. Cluster sampling, we have small groups that are diverse. So you might have the swim team, the football team, the tennis team, right? They all have all grades are in there. Like they're little diverse groups. So they have all grades in there. That's a cluster. And then you just randomly pick a certain number of clusters. So you randomly pick a cluster and that survey everyone in it, right? That was your big idea of the cluster sampling. So I don't know, you guys. I really don't think they're going to ask you like multiple choice. I knew they were going to ask you to identify, but on FRQs, I don't think they're going to have you. The only reason they might have you do this is maybe they have you tell how you would design a sampling method. I mean, I haven't seen that on any of the practice ones, so I just don't know if they're going to make you design a sampling method and describe how you would do it. Um, but they could say to you, why is this stratified? Or why is this simple? Random sampling. Or why was this a cluster sampling? So knowing the difference so you can talk about it would be good. So remember, cluster, main thing, they are very diverse groups. They are mini populations. Think of Austin Powers and Dr. Evil and Mini-Me, right? They are mini populations, and we doesn't matter which one we get then. So there's your main sampling designs review for chapter 12. We then talked about bias. I already put that in another video when I went over one of the problems. So when I went over one of the practice problems, I talked about the bias again. So there's only really three main ones you're going to have to worry about. Um, Probably non-response. So maybe the only bias I think you guys will have to refer to in a test is maybe the non-response, where you have people that don't complete it, and maybe they're somehow different from the people that do complete it. Um, Response bias, where they do complete it, but they somehow don't tell you the truth. Um, so, right, they somehow aren't honest at their answer, and they cause it to be off. Or so those are the two that we talked about the most. I'm trying to think. Under coverage is when you didn't allow everyone to be chosen, so then that might make your sample not look like your population. And then a voluntary response bias. I'll bring this up with today's coronavirus topics. Voluntary response bias could be, there's a lot of studies out there right now, response bias and social desirability, but they seem pretty. But yes, they are very similar, response bias and social desirability bias. So on the AP exam, if it's something like that, you can just talk about response bias. So anytime they are very similar, they are not going to, they think that you've only been taught response bias. So just say response bias when you're referring to it, how they're not being honest or they're not telling the truth or they know you don't want that answer. It's the same sort of thing. Um, Social desirability bias is like you know more than normal people know. Yeah. Um, Voluntary response bias is when you actually have people that self-select themselves to be in your sample. So you put out like a survey right online and you have people do it. That's voluntary response bias. You didn't choose the people to pick your, like in a non-response bias, you have chosen, okay? You have chosen the people to be in your sample. You just have people that didn't respond to it. That's non-response. Voluntary response is you did not choose the people. You didn't choose who got to do the sample. Anyone who wanted to could do it. That's voluntary response bias. And right, usually those are a little bit off toward the negative side. So we usually, um, yeah, we usually don't want to use those. Right now in coronavirus, I've seen that being used. They're trying to figure out how many people have had the coronavirus in their community, and so they have people volunteer to take the antibody test to see if they have the antibodies, and then they come up with a proportion, and they use that to come up with the proportion for their community. But if you had people volunteer to come give you their sample, let's think about it. Who would volunteer to come give you their sample? Probably people that think they've had it. So if someone had no thought that they had it, so why would they waste their time and go do a sample for antibody test? So probably people that think they have it would take the antibody test. And so I think our percentage that we would get in our sample would actually be higher than the true answer. So that's the bad thing about voluntary response. I had to figure that all out just by thinking about common sense, but I think it will be higher. Remember when you talk about bias, if they ever ask you about bias in a problem, um, talk about direction. So talk about which way you think it's biased if they ask you to talk about biased. So that's something to make sure. So I think in that example I gave you, I think it would be we would have a higher number than we really would have in our society. If our researchers had picked a random number of people in our community and then contacted all of them and then had them take the antibody test, that would be better. That would be the way you should do it. The USC study I put on my Twitter a few days ago, they did a random sample of like 868 people in LA County. They didn't just let people volunteer to come take the antibody test. They sent the antibody test to 868 people who they had picked out of a random group in the LA County to figure out the percentage in LA County. So I trust those results way more than when I read about a study where they just had people volunteer to come in and do an antibody test. I can't look at that at all. So that's in today's stuff, what you see. So there's chapter 12. Chapter 13, you guys, was just your block design. Um, so chapter 13 was your experimental design. There wasn't a whole lot of new stuff in there. Um, just remember in experiments, why do we do experiments versus studies? Experiments help establish cause and effect. Remember? Establish, forgot the L. Establish cause and effect. So as long as if you want to do cause and effect, right, you need to run an experiment where you have a control group and your treatment group, and then you can compare the results. Um, so that's your main part of why we do experiments. So um, this is where I want to go over inference a little bit. what you can judgment call, because this could be a question on a multiple choice. I mean, on a FRQ. What is your call that you can make? What is your judgment you can make? Well, okay, if we take a random sample from people and we just did a study, didn't do any treatments, then we can assert our whatever we're measuring. It could be the number for the population. Our measurement can be inferred for the population, right? If you do a random sample. If you don't do a random sample from your population, then whatever you did in your study, we can't infer it to the population. I didn't do a random sample. Okay, so if we did that antibody test, how many people have had coronavirus? If they didn't pick a random sample to get their proportion, then there's no reason I'm saying that that's the number for the true population because I didn't do a random sample. Okay, if you do random assignment, and you have treatments, so experiment instead of a study, then we can infer cause and effect. Now, here is the little wrinkle. There's a little wrinkle in this. Okay, most of the time when we do experiments, we have volunteers. If I have volunteers to my experiment, then I cannot infer that the cause and effect that I figured out, I can't infer that it will work in the whole population because I didn't take a random sample from the population first. If I would have taken a random sample from the population, then did random assignment into my experiment, when I do cause and effect, I could show that it even works in the population. Okay, but most of the time when people run experiments, they're not trying to show that there's cause and effect in the whole population. They are usually trying to show that there is just cause and effect, that this vaccine works versus the not having a vaccine, right? Just cause and effect. We just want to prove the vaccine works. We don't want to prove it works in all of society. We just want to prove it works. So we do volunteers, random assignment, and we prove that the vaccine works, cause and effect. If I wanted to then do, okay, let's prove that it works in the whole population, I would not be able to do it with volunteers. I would have to randomly pick people to be in my experiment. And then once I randomly picked all my people, and it looks like the population, right? It's representative of the population, then I randomly assign into the groups. Um, then I could do cause and effect for the whole population. So if we're doing a clinical trial correctly for the vaccine, we would get a random sample of Americans, ages, genders, right? All these different things, risk factors, right? We'd have a random sample, then we'd randomly assign them to the vaccine and placebo, then we'd measure at the end, and the vaccine works, and did it work for the whole population? Okay, but they probably already ran a trial before that where they just tried to see if the vaccine works. Um, that's probably the first set of trials, and then they get to the second set of trials, which is why it's a long process. Um, so if we were to conduct an observational study, we can establish that there is a relation, but we can't say there is cause and effect. That is right. You are right on. You can say there is a relationship, but you cannot do that there's cause and effect, right? Just like when we did linear regression. Right on. Okay, so experimental design, you had completely randomized. Completely randomized. That is just when you take your groups and you separate them into your treatments and you randomly assign. That's it. And then you compare them. Okay, that's probably your biggest, right? design, completely randomized experimental design. And then we had block design. Block design, okay? Remember, block design is where we purposely separate, just like stratifying. Oh, purposely separate first into groups, then randomly assign to treatments. Try not to hit my video over there. Okay, so purposely separate into groups first. So like, let's say we were doing a vaccine trial for this, and we thought, I think age of patient might affect it. So if you really think age of patient affects it and you want to guarantee that you're measuring that, you will first separate your people into their ages categories, and then you will randomly assign from each age group to the treatments and the control group. So then you will just compare each age group to itself, right? You're controlling the age variable. So that's why it's called a block, because you are blocking the age variable from affecting your response. So that's your block design. And then remember, we had the paired design, paired design. Remember when you block someone with themselves. So you give the person both treatments. Yes, perfect. But the blocking is what stops confounding variables. And that might be a question. We should write that. Blocking helps control confounding variables. That would be a great answer if they asked you why you did block design. Okay. So now, most of the time, right, confounding variables, we don't know what they are. So if we don't know what the confounding variables are, then we have no way to block them. So in order to block, you sort of need to think about it and think about what could be confounding variables. Now remember, confounding variables are variables that are out there in the world that affect the response variable that we're measuring. And we're trying to think of what they could be. Because you have your treatment, right? You have your X variable, and it affects the Y variable, okay? But a confounding variable is something out there, and if we don't think too hard, we don't think about what it could be, there could be confounding variables, and those confounding variables also, right, could affect the response. And it might not be the X, it might not be the one that we're controlling. It might be this confounding variable that's affecting the response. So yes, blocks help control the confounding variables. But in order to control that confounding variable, you have to know what it was. So you'd have to think, is age going to affect my vaccine response? Is gender? Is what about ethnicity? Is ethnicity going to affect the vaccine response? I don't know. Those are things that scientists would have to think about. So blocks help control confounding variables. Good one. Thank you for pointing that out, because that is a good question right there. Okay, so we got chapter 12, we got chapter 13. Okay, let's look at the test questions from that test. So just go over real quick. I won't do them all, but we'll just talk about it and what you might see. So remember this one? You have the sun coming in. We're trying to measure these two different types of windows. We had windows type A and windows type B. And we're trying to see which one was better. So we had to figure out a way to put them in the house. So they told you to do a randomized block experiment to compare the heat gains, so clearly indicate your blocks. Remember, the right answer on this was the best thing to do was to separate into your different directions. So block 1, I would have put like 2, 3, 4, 5, all the east window boxes. Block 2, I would have put like 6 and 7, the south. Block 3, I would have put like 9, 8, 9, 10, 11. And block 4, I would have put like 12 and 1, the north blocks. The blocking design is what stops the confounding, yes. So this will help control the sunlight. The sunlight was the confounding variable on this one, if you really thought about it. So direction would be important because which direction you're at, you probably get more sun. The east gets more sun probably in the west than the south and the north do, depending on time of year, I guess. So there's my blocks. You would have to say why you picked those blocks. So I would have talked about how sunlight from different directions will affect the heat gain in the window, and we're trying to measure the heat gain. So that is sort of our response variable. So you're going to want to say, how does that variable affect the response variable? You say, oh, well, sun direction will affect heat gain because some windows get more sun than others, right? Just putting it into common sense terms. That's all they wanted you to do on A. I remember a lot of people were confusing it and they were doing part B on A. That's all they wanted you to do. They just wanted you to pick designs. And then if you go to part B, that was where they wanted you to describe how you would do the random assignment. And this was totally up to you, how you would assign the randomness to the blocks. So I would have done, right, I would have probably put the box numbers in a hat, right? Easiest thing to do. Box numbers in a hat. Remember, you need to shake it. That makes it random. And then I would pick 2 numbers and they get window A. The other 2 automatically have window B. Right, so you needed to show that you understood that you want equal number of window types in the 2 blocks. That was something that was important. I said I was putting all the numbers in a hat. Remember, that's probably the easiest way if they asked you to do any describing of how you would do it. You would just say you put the names in a hat, you put the numbers in a hat, you shake the hat to get the randomness. You could do a number generator too, but usually the hat is quicker to describe than the number generator. So I would just use your hat again. So that was that one. That was about designing it. This one was identifying. So probably I think you're more likely to get a problem like this where you're just identifying. So they're investigating the effectiveness of a fungus to control the spread of an insect. So they have 4 different concentrations of fungus mixtures, the 0, 1.25, 2.5, and then they said they're going to put them in 20 containers. Equal number of insects will be placed in the 20 containers. The group of insects will be sprayed, 1 to 4 mixtures, and then they'll record the number of insects that are still alive after 1 week of spraying. So the treatments are, what is getting the treatment? What's getting the fungus? Well, the flies are getting the fungus. A lot of people said, oh, it's the flies. It's actually the containers of flies. So a better answer than just the insects would be the containers of insects, because we're applying it to the container. And then we're measuring how many are still alive after a week. So for each container. So the container was the experimental units. Remember, experimental units are what are getting the treatments. The treatments on this one you would just describe. It's these 4 fungus concentrations, and the response variable we are measuring how many are still alive after a week. So probably the proportion of survival would be my response variable. Or my statistic. My response variable, how many are still alive in each container. Does the experiment have a control group? Yes, because it had the 0. So that was your control group. Treatments are the combinations of factors and levels. You're right, Buck. That is right. Treatments are the combinations of factors and levels. Perfect. Describe how the treatments can be randomly assigned to the experimental units, so each treatment has the same number of units. This is again like part B of problem 1. Describe how you would do it. So there's 20 containers. There's 1, 2, 3, 4 different concentrations. You could put all the numbers in a hat, 1 to 20. I would number, first you'd say you numbered all the containers 1 to 20. Then you could say that you put them in a hat, all the numbers. You shook the hat, and you take out 5, right? I would take out 5 numbers, and those 5 numbers would all get 0. And then I shake that and take out 5 more, 1.25. Take out 5 more, 2.5, and then the last 5 left in the hat are going to get 3.75. So you just describe how you do it. A lot of times I just use the hat. And then the last problem on that test, remember, were these apartments where we were testing carpets. For convenience, the apartment building owner wanted to use a cluster sampling method in which the floors were the clusters. Describe a process for how you would randomly select 8 different apartments. So since in a cluster sample, you randomly pick the cluster and then you get everyone on that cluster, that means when we randomly picked a floor, we would get 4 apartments. We need to get 8 apartments. So I randomly need to pick 2 floors. So I could say that I put the floor numbers in a hat, shake up the hat, and I randomly pick 2, and then I give every apartment on those 2 floors the carpet. There's a description of how you did the randomization, right? A lot of people were not doing that one correctly. I remember that one. They were doing it incorrectly on that one. So the clusters have already been identified. So usually if they want you to do a cluster sampling, they probably have identified what the clusters are for you. And then you need to remember that when you pick a cluster, you just pick a certain number of clusters that you need, but everyone in that cluster will get surveyed, or will get this one was carpets. And then they asked you on this one about a confounding variable. They said it would have been better to do a stratified random sample of 8 apartments rather than a cluster. So a stratified random sample of 8 might include 2 random apartment children and 6 with no children. Why? What would be a statistical advantage of selecting a stratified sample as opposed to a cluster sample? So they were basically trying to talk about there's a variable out there that we're not addressing, and that was children in the apartment. And when you did cluster sampling, you were not guaranteed to get children in your apartment, because if you would have picked the 3rd floor, there's no children. 6th floor, no children. So it was possible, 4th floor, no children, that you could get no children in your sample. So by stratifying into apartments with children, apartments without children, and then picking however many you want, they were going to pick 2 from with children, 6 from without children. You're guaranteeing that children are in your sample. So the carpet is getting tested. Why would that be important? Because the carpet probably has to stand up differently when children are in the apartment. Just like if an apartment had pets, I would want to have pets guaranteed to be in my sample, because I want to see how the carpet does when it's abused a little harder than in a normal apartment. So pets and children might abuse carpet a little bit more. So that was a harder one to answer, but that's more typical of what you might see. Like, how is that better, right? That's more typical of what you might see. So there was your questions for that unit. That unit, you guys, more just important that you understand the different ones. Probably more important that you understand the differences and why things are important. That's what I think. I sort of think that it's more likely that it's about the whys. I just think this test is going to be a lot more about your whys rather than just your whats. So there's the chapter 12 and 13 cram session. Now I can go to, I'll go to the early stuff. Okay, I'll go to the early stuff. So let's go into chapters like 2 through 6. That was the very first unit. You guys did chapters 2 and 3 over the summer last year, which were your categorical data and finding percentages and that kind of stuff. And then we did chapter 4, 5, and 6 in class. So this is the most important stuff in chapter 2 through 6 is how you describe data. Here we go. So describe data. Okay, you guys, I think you're going to get a describe data. I think one of the parts on the FRQ will be, hey, what does this look like? They might give you a histogram, right? They might give you a dot plot. We've had these on all the practice ones. They might give you they could give you a stem leaf. We never know, which is just like a sideways histogram. Um, they could give you a box plot, which they did do on one of the problems. So the ones that we've had on our problems right now, we had this on a practice problem, we had this on a practice problem, and I don't think we had a histogram on a practice problem. We had dot plot and a box plot on the 2 practice problems where they did um, the quantitative data. So when you're describing the data, remember, we need to describe shape, right? Doesn't matter which one I get. I can describe the shape. Now, some are better than others at describing certain aspects of the shape. So remember, box plots, you can't really see modality. But stem leaf, I can see modality. Dot plot, I can see modality. Histograms, I can see modality. So shape in a box plot, probably you're just going to talk about skew or symmetric. That's all you can really say in box plots. Okay, is it symmetric? Is it right skewed or is it left skewed? Remember, the skew is where the tail is. So this right tail on the right, that is right skew, not where the hump is. Okay, don't mess that up. It's where the tail is. Okay, so that is a right skew. Okay, if I put the tail over on this side, right, that is a left skew. It's not the hump, it's where the tail is. Okay, that's too easy to mess up. Okay, so you're going to do skew, symmetric for your shape. On these ones, you can talk about skew, symmetric, and you can also talk about modality. So all of the other ones, right, you can refer to both and both. Okay, so all the other ones were good. The only one we can't really talk about modality is the box plot. Remember, modality is either unimodal, if there's only really one center, could be bimodal. I don't think they'll do anything higher than a bimodal. It could be multimodal. I don't think you're going to get a multimodal. So probably you're going to get a bimodal if they're going to change it. Okay, probably you're not even going to have to worry about it because it's probably just going to be unimodal. So anything, these 3 talk about that. So that's first. Okay, so first thing you're going to talk about shape. Shape. Um, shape, right? First thing we talk about, shape. Okay, second thing we talk about way back in that unit. Second thing we're going to talk about center. I like to bring up the center. Okay, your choice of what center you want to use. Um, I will tell you that a median is pretty quick if you're given dot plots and box plots, because the box plots that's on there. Dot plot, count the dots, find the middle one. Stem leaf, count again, just like a dot plot. Histogram, a little harder. You won't know the exact median on a histogram. You'll just know it's inside of this box. So counting is good. So you can use median or mean. I mean, they might give it to you, so you might not have to do it yourself, but you could do it yourself if you needed to. Um, If they don't give you, you can just estimate it too, you guys. I don't think they're going to punish you that hard. You don't have a they're assuming you might not have a calculator. So if they're assuming you might not have a calculator, they're not going to punish you for giving an estimate of where the mean or the median is. Okay. Median, we can be exact because if they give you a dot plot or a box plot or a stem leaf, you can count. Those ones, and a histogram is the only one where I don't really know exactly. Okay, but the other three, which is probably why they'll lean to giving you one of these, you can tell from that. So center, shape, okay. Third thing we're going to talk about is we're going to talk about spread. Um, okay, so this is, I'm taking some advice here from the practice test they've given you. And from what I've seen on the practice test they've given you, um, they are leaning toward you um, doing range actually, which is the easiest one to do. Um, so range could use IQR, um, could use standard deviation, but come on, let's be real. Who's going to use standard deviation? No way. Okay, so range could do standard deviation, could do IQR. You're probably not going to do, okay, um, standard deviation. Come on. So remember, if it's a box plot, IQR is awesome because it's the box. So really quick, really easy. On these two, stem leaf and dot plot, it's a little harder. You got to count out to Q3 and Q1. So remember IQR, interquartile range, is third quartile minus the first quartile. I put this on a review video for one of the problems that we had. Um, remember the third quartile is the 75th percentile and the first quartile is the 25th percentile. So remember that 50% of the data is between the third quartile and the first quartile. IQR is how far that is. If you subtract those two numbers, what is that distance? That is called the interquartile range. You don't have to actually tell me the interquartile range. You could tell me that it goes from Q1 to Q3. You could tell me those two numbers. That would be okay too. Just like on range, you can say, oh, the numbers range from 0 to 10. You could do that. You don't have to give me, oh, the range is 10. You could tell me it goes from here to here. That would be fine. They're not going to punish you. And then the last thing we need to do, right? The last thing is unusual features. So anything, whoa, 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 whoa. Unusual features. So when I talk about unusual features, I'll just put unusual U. When we talk about unusual features, right, it could be gaps. Where are the gaps? Make sure you do the locations of your gaps, um, and or outliers. On a previous video, I went over the outliers. Remember outliers, the boundaries are Q3 plus 1.5 IQR. That will be the upper boundary. So that's the upper fence. If you're outside of the fence, then you're an outlier. And Q1 minus 1.5 IQR would give you the lower fence, right? So those will be your outliers. Remember on box plots, they'll just show up as dots. I love it. Give me a box plot. I'll show it up as a dot. So you talk about any gaps, where the gaps are, and outliers. Don't forget when you're describing all this process and you hit these four things, don't forget context. Oh my gosh, it's so easy to forget context because you guys are stressing, you're going fast, and you just forget to put in units. So what helps me to remember context is always think about what are the units, okay? Because if I have a tendency to put in the units, then I will have a better tendency of putting context into the problem. Okay, so super, super important. You're going to definitely get a describing, I think, data. That's a great place to start on a problem as part A is like, here's a histogram, here's a box plot, describe what you see. And you have to go through and do those four things. So be ready for that. I think that will probably come up. Um, what else was in that first unit? Um, resistant to resistance to outliers. So remember, means if you have unusual points in your data, remember it's not good for means and standard deviations. So medians are resistant because remember they don't get moved by tails and outliers. IQR is good because the quartiles don't move that much from outliers. So median and IQR resistant. Not resistant, what does get affected by outliers and skews? Um, the mean definitely gets affected by outliers and skews. The standard deviation definitely gets affected, right? Because it's every data point's in the calculation for standard deviation. Um, and what else? Range. Range definitely gets affected if you have an outlier. So those things are definitely going to get affected. So that might come up in a question. I don't know how they would ask that. Maybe they change a data point on you and ask you what happens. So remember, um, medians don't care about the data. They just care about location of the data. So remember, location of a median is always n plus 1 divided by 2. Number of data points plus 1 divided by 2 will always tell you where the median is located. So that came up in that first unit. In our categorical data, what was important? Bar graphs, we made some bar graphs, segmented bar graphs when you stack them. Independence, which we brought in later on in probability. Remember, if the bar graphs look different in the two groups you're comparing, if the bar graphs look different, that would mean that they're not independent. If they were independent, the bar graphs would look about the same because it wouldn't matter what group you were in. So we talked about that. Marginal distribution is for the totals. Conditional distribution is when you're looking in the table somehow. So remember that. Marginal distribution, if they say, I don't think they're going to use it. I haven't seen it on any practice test. Marginal distribution is when they somehow want you to figure out percentages from the totals. And then remember conditional distribution, conditional, just some vocab words. I don't think you're going to get tested on it, but conditional distribution is when the percentages are from rows or columns in table. So not from the totals. So that, some vocab from chapter 3. Chapter 6, remember, was doing your normal distribution stuff, which we did all year, so I don't think you're going to need a total need to cram on that. Your normal CDF command, remember, we're always going to label because I want you to get full credit. So you got your lower boundary, and then you got your upper boundary. Where are you finding the area? And then you're going to label the mean is this blank and the standard deviation is this. Remember, label so you get full credit. Okay, if you use any normal calculation, make sure you label what everything is with the right symbols. Lower, upper, I think you could probably just put L and U and it will be totally fine. But label if you use normal CDF. Remember, inverse norm is when you're going backwards and you label the area. Oh, I've forgotten. Hold on. Inverse norm, I gotta look. It's been a long time since I hit inverse norm. You put the area to left unless you have the new calculator, right? And then you put in your mean and then you put in your standard deviation. So that's the older calculator. And the newer calculator, you didn't have to put area to the left. I downloaded the new one onto my calculator on the TI website. Yeah, I can do left, center, right now, but I'm assuming you guys didn't do that and you just still have to do left. Um, so there's your inverse norm command. There's your labeling of that. Your z-score in chapter 6, we learned about z-scores, right? How to compare two groups, two data points to each other that are in two different groups. Remember z, what is a z-score? It's the distance your point is from the mean in standard deviations. So remember, the z-score is your distance away from the mean in standard deviations. Okay, if you're 1.2, that means you're 1.2 standard deviations above the mean. If your z-score was a negative 2.4, that meant you were 2.4 standard deviations below the mean. Remember, the positive negative tells you which way it was. Negative, you were lower. Positive, you were upper. You were higher. So z-scores, most of us didn't use our z-scores that much because we would use normal CDF. Remember, sometimes if you want to get a z-score, you can put in 0 for your mean and 1 for your standard deviation. But that was all chapter 6. So chapter 6 was all your first time you ever learned about the normal distribution. Chapter 5, we learned about comparing two quantitative distributions using box plots. So chapter 5 is mostly about box plots and comparing them. They might have you compare two groups, right? Because I think one of your questions is going to be a one group inference and the other question is going to be a two group inference. So if it's two quantitative pieces of data, they might have you compare two box plots. Could happen. Remember, when you compare two groups, to write comparative statements. Don't say the mean of this group is 5, the mean of this group is 6. Say the mean of this group is higher than that one, 5 and 6, right? So write a comparative statement. If they say to you compare, write a comparative statement. If you see that word, make sure you write comparative statements. Don't just tell me the two numbers and list them. Okay, you need to compare them. I see students mess that up. They're easy problems and they mess it up because they don't actually write a comparison statement. They just say what all the numbers are and they don't compare them. So if you see compare, make sure you do that. Oh, again, it will be an early part of a problem, probably an A or a B, maybe a C. So that's your describing distributions. What else? Left skew, right skew, we did that. Symmetric. Remember never to say normal. Say approximately normal whenever you're going to say normal. Remember standard deviation. I wrote it in our last video. Make sure you watch it. I talked about it being not, don't say it's the average deviation like I said it in class, because I found out that's not very accurate. So you should say it's the typical deviation or the typical distance that each point is from the mean. That's better than average. And then so that takes care of that unit. The only other unit that we haven't covered with our review yet is the linear regression unit. So let me go over some problems on this unit before I get to linear regression. So let's go back to your test on this first unit and let's look it over. I think there's a compare one on here, so I think we can look at it. So this one, size of 20 rooms in a student residence hall at a certain university are summarized in the following histogram. Perfect. Based on the histogram, write a few sentences. Typical question right here, you guys. You're ready. This is definitely, I think you're probably going to have something. So I would have said bimodal, slight left skew, maybe symmetric. It's not that bad on this one, but definitely bimodal. There's a center, it looks like, between 150 and 200 square feet, and there's another center, looks like between 250 and 300 square feet. So it looks like there were two like main centers of these residence halls. Um, and then what is the range? The easiest thing on spread is to just say, hey, the residence halls range from 100 square feet to 350 square feet. That's quick, that's easy. I didn't have to sit around doing IQR. So you guys, range is fine. When you describe, you can use range. That's totally fine. You got the spread. And then we did center, we did the shape. Anything unusual? The bimodality is a little bit unusual, but I don't see any outliers. There's no gaps. Um, that's about it. So nothing really that unusual in that one, just the two centers. But I talked about the two centers earlier in the problem, and I brought context into it. So that's a good one for that. Then they give you the summary, which is what I think is going to happen on the AP exam. I think they're not going to make you calculate anything. I think they're going to give you everything, and you're going to have to interpret. So in this one, we were making the grid and making a box plot. So this one, we were just turning this into a box plot. So remember, it's been a while since you guys have done this. Remember that the median is the middle line, so 253.5. There's 250, maybe like right here, 253.5. Q3 is 292, so maybe like right here for Q3. Q1 is 174, so there's 170, 174, maybe Q1 like right there. So there's my box. Sorry, I can't draw very straight. My box is right there. And then max was 315. Now wait a sec. They said check for outliers. So they were giving me a clue. So 292 minus 174. Did they already give me? I thought maybe they gave me the IQR. They didn't. 292 minus 174. Yeah, I can't subtract in my head. Is 118 times 1.5. We have 177. Okay, so it's going to be 292 Q3 plus 177 and 174 minus 177. So that one's -3. That's the lower fence. We don't have anything past down there. The upper fence, 292 plus 177. 469 for the upper fence. No, so I don't see any outliers. I checked, but I don't see any outliers. So we did Q1. Make sure I did it right. I'm scared because I thought there would be an outlier. That's right. That's right. That's right. Yeah, yeah, that looks right. So no outliers. So go to 315 for your whisker. So that whisker goes to there. And other whisker goes to minimum 134. Maybe like right there. There's your other whisker. There is my box plot. So refresher on box plots. Um, and then on the bottom here, what characteristic of the shape is apparent from the histogram, but not on the box plot? The modality. You cannot tell there's any bimodal going on here when you look at just the box plot. So see how different that is? The box plot can totally hide some information that you would have been important. There were two centers, right, of these residence hall sizes. So sort of important. Okay, here we go. This is your comparing that you wanted. So here's your two box plots. They want you to compare. Remember, we had to write a few sentences comparing. So remember this one. They were so hard to get full credit on this. You had to say, okay, let's compare the centers. Corporation B, 52 maybe thousand, median. Corporation A, median is around 52. So I wouldn't have said, hey, both corporations were 52,000. I would have said, Corporation A and Corporation B has about the same median at around 52,000. I compared them because I said they're about the same. So that's my comparative statement. Now I should compare the spreads. Well, let's see. Corporation A looks like it's a little more spread out. It goes from like 35,000 to maybe like 78,000. And Corporation B goes from about 41,000 to 60,000, right? So Corporation B has a much smaller spread range than Corporation A. So the range, I would have done range again because range is easy. Could you have done IQR? Yeah, you could have done IQR. You could have said the IQR at Corporation A is like, what is that? That's about 47. That's about 56. That's about 9,000 for the IQR there. And the IQR here looks like about 47 to about 53. So maybe about 6,000 IQR here. So yeah, Corporation B's IQR is a little bit smaller than Corporation A, but the range is way different. Corporation A has 2 outliers. Corporation B does not have any outliers. Um, at the high end, 72,000, 78,000, right? So I compared the outliers, I compared the spread, I compared the center. Um, and their shapes, well, their shapes look definitely Corporation A has a right skew because of the outliers. Um, it's hard to tell on that one. Corporation B looks more symmetric, maybe a slight left skew. Um, so you could then compare the shapes. So when you're doing comparative statements, compare the center, compare the spread, unless they only ask you for one, right? They might just say, hey, just compare the center. Then do the spread, then do anything unusual, right? And make sure you compare your shape. Um, so just like we did on describing, I'm just comparing the two. So that was a really good problem. It was really hard to get all the points on A. A was tough to get an E on. So, right, they give you something like that. Yeah, it could be tough to get an E on that. Okay. And then the next one, suppose that both corporations offered you a job for 36,000 as an entry-level accountant. Based on the box plots, give one reason why you might choose at A. So they're going to offer me 36,000 for entry level, both. Why would I want to choose Corporation A then? Well, Corporation A, this is not, what is this? This is the, still, these are the people that still worked at the corporation 5 years later, right? Everyone starts at 36,000 at these two corporations, but this is 5 years after that. So there are some people at Corporation A that are still making about the same as what they started 5 years ago. They didn't get a raise in 5 years. That sucks. Okay, so I wouldn't want to choose Corporation A for that reason. But these two means that there are two accountants at their firm that make up to like 78,000 because they were, I guess, so amazing good that they moved up. So Corporation A I might want to go to if I have high confidence in myself and think that I will work better and harder than everyone else because I have the potential to make a lot more, 70 to 80,000. Um, Corporation B would be a great place to go to because I know that no matter what, I'm guaranteed to get a raise. So even if I'm the worst employee that's still working for them in 5 years, I'm at least making 41, 42,000. That might be a reason to take Corporation B. So some of you might have said the spread was less on B, but how does that an advantage to you to go to B? Um, this was the real advantage. The lowest number here was higher than 36,000. That was a disadvantage for Corporation A. The advantage for Corporation A were the two outliers. So you would talk about what on the graph is making you make the decision and then put it into context of that problem, what that means in real life. That could be a problem. Those are nice. Those were actually, I remember scoring those. They were hard to get a good score on. And then the last problem was your normal distribution problem. We can go over this because it's been a while since you guys have done your normal stuff. So the time it takes a driver to react to the brake tail lights on decelerating vehicle. So mean is 1.25, standard deviation is 0.46, and it's a normal distribution. Okay. What percent of reaction times are between 1 and 1.75? So this is exactly what I would write on my test. Normal, CDF, you're allowed to use the command, and then I would put lower 1, upper 1.75, mean was 1.25, and standard deviation 0.46. That's exactly what I would write on my test. It would look a little nicer than that because I'm writing with my normal paper. 1 to 1.75, 1.25, and 0.46. 0.568. Now, here's the thing. This year's test, we should be able to do without a calculator. If that is one of their requirements this year, is that their questions they gave you had to be able to be done without a calculator, I have a feeling if they give you a normal distribution one, it will end up on the lines. Remember, okay, things you need to remember. I put on a week or two ago, I put the formula sheet. Print the formula sheet out. Print the T-chart out. Print, right? You need to have those ready to go. They are not providing you them on the test. You need to have them printed up and next to you or on a screen next to you. Okay? You could do this one by hand if you had the charts. You could get a z-score and then you could look up the z-score on the chart. So you could do it by hand. How could they make it easier? What if they make the z-score 1 or -1 or 2 or -2? You could use your 68, 95, 99.7 rule. So for all the students that don't have access to their calculators, right, they could make the numbers so perfect that they end up on the standard deviation lines. Remember, 68% of data is within one standard deviation. 95% of data on a normal distribution is within 2. And 3, right, is 99.7. So they could give you, right, a number on the line. You don't have to do it by hand, though, guys. You can use your calculator. It's just they're enabling everyone to be able to do it. So numbers probably won't be too bad. The worst 3%, slowest, are longer than what time? So on this one, the slowest times, if this is my normal distribution, that's the best I can do on this, you guys. If this is 1.25, I would like to know where the slowest 3%, that means where is the slowest? So this percentage right here is 3%. So I'm going to go to my calculator. I'm going to go to inverse norm. I'm not going to put in 0.3. I'm going to put in the area. If that's 3%, the area to the left is 97%. And then my mean is going to be 1.25, and my standard deviation is going to be 0.46. So if you do your inverse norm command, it's been a long time since you've done that. 0.97, 1.25, 0.46, I'm doing left. So 2.11 is the actual point. And this will be units. So I better put some units on there, 2.11 seconds. And then drivers distracted while driving have different reaction times than the mean group given, but are still normally distributed with the same standard deviation. If the slowest 5% are greater than 3.0, what is the new mean? So we do not know the mean. So there's like a new standard deviation, new normal. We don't know this, but we do know the standard deviation is still 0.46. And we do know that the slowest 5%, so this area over here, is 5%, and we know that that is 3. So what am I going to do? Well, first thing I'm going to do is find the z-score for that location. So the z-score for that location would be inverse norm, and area is going to be 95% to the left. The mean is, oh shoot, we don't know the mean. We're going to make it 0, and we're going to make the standard deviation 1. Remember, if you want the z-score, we put in 0 and 1. That's how we do it when we don't know one of those. So area is 95%, 0 is my mean, standard deviation is 1. My z-score would be 1, oh, it's right on. 1.645 basically. So there is your, so that's like the 95%. Oh my God, what am I thinking? Yeah, that's right. So 1.645 is that location, right? 95% was to the left. Yeah. And so we take that z-score, and remember we make it equal to the formula I gave you. We don't know the, oh, we do know the x. The x at that point, thought we didn't know it, is 3 seconds. So we know the x at that point was 3 seconds. We do not know the mean, but we know the standard deviation is 0.46. Solve this point, cross multiply, get 0.7566 equals 3 minus the mean, subtract 3, subtract 3. So I get the mean to be 2.24 seconds. So the mean has changed now that we have distracted drivers. It went from 1.25 seconds to now the mean is 2.24 seconds. Um, so that's a little bit tougher. It's been a long time since you've done that. Inverse norm. Will they get anything that tough, you guys? I don't know. That seems a little calculator heavy. You could use the table to look this up if you had the z-score table printed out with you. You guys, it's not as necessary for you to print the z-score table out. The table that I really need you guys to have is this table. Um, you really want to have, this one's not as important because most of you are going to use your normal CDF on your calculator. So that one's not a big deal. But this one you will want, right? For your means and your t-scores. Degrees of freedom are over here on the left, right? N minus 1. And remember, the confidence levels are down here. So if you really needed a quick check, you could look at that. Remember, the last row is your Z's. So those are your Z criticals. Okay, so if you want to use confidence intervals and you want to do them by hand, remember that last row tells you your Z criticals. So 90% confidence level would have been a Z critical of 1.645. That's why I was recognizing that number. It was your 90% confidence level. Makes sense. 90% in the middle, 5% here, 5% there, 100%. So I get it. I get it. I get it. So that table, you guys are going to want printed. Um, and if you want these formula sheets, if you can't remember the stuff, um, I think you're going to remember it. I don't think you get, and I don't think actually, I really don't think you're going to have to use them because that's a lot of calculations to do by hand. So I really think they're going to give you p-values already. So I don't know how much you're really going to need this. Um, we didn't even do chi-squared, so don't even look at that. But your binomial distribution, there's the middle, the mean, and the standard deviation. And if you're geometric, they gave you there's the middle and there's the standard deviation. So I mean, those you never know. You never know on those ones. Maybe I would use those. Remember, the mean expected value of a discrete random variable is when you multiply the probability times the random variable. We didn't really do standard deviation by hand ever. I let you use your calculator when you put your data in. And then there's your probability formulas. Oh, I wanted to give you a Bayes theorem problem. That's what I wanted to do. I'll have to find it. I put it somewhere. I'll look on my phone. I put it somewhere. So that one. Okay. So that test done. Okay. Done on unit 1. Okay, guys. So we've done a lot. So the last thing that we haven't reviewed yet is your linear regression. I just don't. I haven't seen any practice problems where they've done linear regression. So I just wonder whether they're going to give you one or not. I mean, they're usually pretty easy, um, but I just don't know. Remember, linear regression, You create your scatter plot. You're not going to have to create the scatter plot this year. They will give it to you. Explanatory response. We're looking for patterns, right? We're looking for linear data. Okay, so we're looking for linear. So when you're describing a scatter plot, remember, what do we have to describe for a scatter plot? We have to describe form. Is it linear or curved? So first thing is form. Second thing, direction. Is it positive or negative? Okay. Third thing, we got form, we got positive. Strength. Strength. It's been a long time, you guys. I'm just making this stuff up. Okay, strength, which is where we use, remember, it could be strong, could be weak, could be moderately strong, um, strong. Ah, I put an M. N, moderately strong. Oh, why'd I put a comma there? Moderately strong, weak, or no, right, or none. And remember, we use correlation, so this is where we look at our R, right, to tell us whether we're strong. Remember, strong was like 0.8 or higher. Moderately strong was like between 0.5, 0.8, and weak was usually less than 0.5. Remember the sign. If R is negative, that tells you it's a negative direction. If R is positive, it tells you it's a positive direction. So just by knowing R without a scatter plot, you know what direction it's going. And then anything unusual, right? Form, direction, strength, context, unusual points. I've been saving this question. Does strength only count for linear? Okay, correlation only counts for linear. Okay, you can have strength for a curve. Okay, like if I gave you a scatter plot and it looked like this, right? That's strong for a curve. I'm not going to use correlation. I'm not going to use the R. I'm going to say it's a strong relationship for a curved form, right? But I'm not going to use R. So R correlation is only used to describe linear strength. That's a good question. So we only use correlation to describe linear strength. That's the common layman's mistake, right? Most people in the real world use correlation even when they're doing curves. Would you expect them to ask us to draw? No. What I've been told is that you guys will not be drawing graphs. That takes too long, and so they're not going to have you draw graphs. Every graph that is given will be given to you, because they want to ask you like 8 questions on an FRQ. So if they're going to go A through G, there's no way you have time to do a draw graph. So no drawing. Okay, and then let's see. So that's describing your linear regression, and you got that curved. Okay. That's it for that one. And then remember the next chapter we figured out our line of best fit. Remember, it's called a least squares regression line. Remember, I don't like you to write y and x. It's better for you to write the actual variables, write within words. Don't forget, this is predicted. So on an FRQ, right, if you forget the hat, they might punish you down to a partial from an essentially correct. So don't forget the hat on your predicted. And right, this is your slope, and this is your y-intercept. Again, are they going to make you do it? I don't think so. Um, I think they're going to run the analysis for you, maybe have that where they give you the printout. I'll look on your test question. Let's see if it's on the test question. I think they're going to give you like this. This is what I think. I think since they don't want you to calculate everything, they're going to give you like this. If they give you a linear regression, I think it's going to look a lot like this number. Um, so knowing on this, remember which one was which. Super important. That's why I brought this one up. So remember, this is your constant, so that means this is the y-intercept. Oh, why'd you do that? That's so weird that it did that. So that's, oh, I did it again. It must be a sensitive area on my tablet. So this is your y-intercept right here. And then this was your slope. Okay, so constant is your clue that it's the y-intercept, right? And this should be your x variable. And that would tell me that the number in front of that one is my slope. So I think they're going to give you a printout. The nice thing for you guys, oh my gosh, is because we never got to do chapter 27, you never had to learn about these guys. I know. It's sad. You never got to learn. That's the p-values and the t-scores. I'm so sad about that. But we would have learned how to do those. We would have. Okay, they're just p-values. I'm not going to complicate your life now, but you know, it would have been cool. But there are p-values. There is a t-test for slope. Um, so this line I would have written, remember, I remember this problem. I would have written um, the equation for this line would have been the time, predicted time, so I would have put time with the hat on it, equals 174.4 times customers in line plus 72.95. That would have been the linear regression line, okay, on this problem. Remember, don't forget the predicted and put your variables in words, not x and y. Otherwise, you have to describe what x and y are, and it just takes longer. So this one says interpret the intercept for the least squares regression line. So you guys, if they give you a problem like this, they're just going to have you interpret the numbers. That's it. Interpret slope, interpret y-intercept. That's what they're going to want you to do. So this one, if I'm going to interpret y-intercept, that means if there were no people in line in front of you, it will take you about, right, there's my gray word, about 72.95 seconds, right? These are in seconds. Yeah, to check out. That's me interpreting the y-intercept. Remember, you need to have the gray word when you're interpreting on this stuff. If there were no people in line in front of you, it would take you about 72 miles, or we predict it would be about 72. Right, predict is a gray word, about is a gray word, on average is a gray word, right? Remember, we have to put those words in. They did not have you interpret slope on this one, but I'd love to do one for you. So here's my interpretation of slope. Um, for every increase in one customer, the checkout time increases on average by 174.4 seconds. So for every one increase in one customer, right, that means it's going up by 174. Hmm, interesting. Interesting. If there's no people, it takes you 72 seconds, but for every customer, it added 174 seconds. Um, so that's your interpretation of slope. Remember, the interpretation of slope is your average. Remember, a lot of people forget on average. Um, And remember, it's for one increase of the x variable, and then it's the y variable. Don't forget context. So those are two that I think could show up. I think a problem like this could definitely show up. Identify, interpret the coefficient of determination. So this is your r squared from your graph. Do not use the adjusted. We never use the adjusted. So use the r squared. So that means that 73.33% of the variation. Why'd I put what did I do? I was like looking and not thinking. The variation in time to check out can be explained by the variation in number of customers in line. I don't need the S. Of customers in line. So that's what I would put as my interpretation of the r squared. Remember, the variation of y can be explained by the variation of x. Um, that might come up. Those are some on linear regression. This is definitely the problem that I think you would be more likely to get something like this. But I just don't think they're going to give you a linear regression. I'm going to be honest, you guys. I don't see them giving you a linear regression because if I want to make this a 7-parter, I'd run out of stuff to ask you. You guys don't know how to do inference on this stuff. So you don't know how to use this to do any inference, to do our t-test for slopes. So they run out of questions to ask you if they give you a linear regression problem. So they'd have to like change the problem as they were going through to be something else. So I don't know. That's where I'd be shocked. I mean, you might get it. What I've heard is people are all not getting the same test. So I've heard, you know, my wife does AP Psych. They took that on Tuesday. You guys are all not going to get the same tests. There are different tests out there. There are different versions. So maybe there's a version out there that has a linear regression. I don't know. I just don't think they could ask you a lot more unless they change the problem as they're going. One of the data points is determined to be an outlier. Circle the outlier, explain why. Well, definitely this one is an outlier, right? That's really unusual. There were 3 customers in line in front of you, and it took you way less time to check out than we would have predicted. So, right, that's why it's an outlier. It's way less time. It doesn't even follow the pattern of the line of best fit because these were fairly strong. So if your r squared is 73.33, if we square root that, 0.733, that's 0.856. So on this problem, the r was 0.856, and it'd be positive because this line is going up, so it's a positive. Remember, if this line had been going down, it would have been negative. You would have had to put a negative on there. Because when you square root that, right, it's always going to be positive, but you might have to put a negative sign on it. Oh, remember this is the standard deviation of the residuals. So if you took all the distances from the actual points to the lines, right, remember that was the residual. All those, that one is huge. All those distances from the points to the line of best fit, if you take all those and you find the standard deviation, that's about the average distances away. So it sort of tells you how much those change. So the typical distance away from the prediction was about 200, which seems fairly high. But I think this one's messing it up because this one is so high. Um, and remember, standard deviation is not resistant to outliers. Um, so you know, that's one reason that number could be really high. So there is what I think you're going to have on linear regression, something like that. Very typical. I'm trying to see what else was on this test. The scatter plot, there we go. They just gave you scatter plot. Based on the scatter plot, describe the relationship. Oh, so you would say as height increased, arm span also increased for the 12 seniors. It's strong. I would say moderately strong. It looks linear, right? I have context into it. Then they do this. I remember this one. Oh yeah, I totally remember this one. They draw on the two lines. One was the line of best fit with the data, which is graph 1, and then graph 2 was they did just a y equals x line. So you can see any point that's on the line were equal. They were like the same height as arm span. And if you were above the line, then you were your arm span was higher than your height, which meant you were a short rectangle, what we call. And if you were below the line, your arm span was lower than your height, so that meant you were a tall rectangle. And then if you were on the line, you were a square. So which graph is better to classify? Definitely graph 2 would have been better. Um, count up how many of the 12. 1, 2, 3, 4, 5 were short rectangles. 1, 2, 3, I see 3 that are squares, and 1, 2, 3, 4 that are tall rectangles. And then they said use the best model for prediction. Well, this is not a great model for prediction. This is just the model for us knowing what your body type is. This is our model for prediction. So I should be using this equation when I do predictions. So I would plug in a height of 61 inches into my X, and I would figure out the. Now, remember, I'm going to go over something that could be tricky on this. Times it by the height, 61 inches plus 11.74. I get a predicted arm span of 62.04. Now, they could ask you for the actual arm span if you know the residual. So you could say, oh, their height is 61. That one looks like the 61. The residual was actually, right? Pretend you didn't know that. Pretend you just knew that distance was 4. Okay, you could add 4 to your predicted to get that one. So there is your linear regression, you guys. I think your linear regression is going to look like this. If there's one that shows up, it will probably look like this. Graph's already given for you. Printout is already done for you. You're just going to be in charge of interpreting, writing interpretations, describing, maybe come up with a prediction. Remember, like this one. I love this part. This wolf problem. This was like from 3 or 4 years ago. I love the wolf problem when they make you use the line and to come up with what was the weight of the actual weight of the wolf. So they told you one wolf had a length of 1.4 meters, but a residual of negative 9.67. So remember, you had to take your model that you had for your wolf, and you had to plug in negative 16.46 plus 35.02 times the length 1.4. So you would plug in your 1.4. You show that. It's an FRQ, you guys, so make sure you show yourself plugging it in. I don't want you to miss points for that. So I get 32.568, and that is going to be in kilograms. That's our predicted weight for this wolf. Well, this wolf had a residual of negative 9.67, so that meant it was lower than our predicted by that amount. So we're going to subtract 9.67 kilograms from the predicted weight. And so our actual weight of this way underweight wolf is 22.898 kilograms. Oh, that wolf needs some food. Okay, so that wolf is much lighter than a normal wolf. How do you interpret these words? Positive meant as x increases, y increases, but you would do it in context. As x increases, y increases. I would say as in context, length increases, weight increases, right? That's your, what is linear? Means that the points follow a linear pattern, which means the rate of increase, right? Which means if just think about your math skills, it means your rate of increase is a constant because it's a linear pattern, okay? And then strong meant that all the points closely follow the line of best fit. So they follow the line of best fit closely, right? That would be what our link for strong is. So that was just some in context um, questions. So there's that unit. So linear regression, done. That's your important stuff for linear regression. So I think we have hit, if you watch all the videos I have made, you guys, we have hit everything. I wanted to give you a Bayes theorem problem, so let's do a Bayes theorem problem. I'm just going to make one up here. Okay, coronavirus style. Okay, so um, let's say 5% of people have had coronavirus. So about 5% of people in our society have had coronavirus. We're just saying this is from the LA County USC study that I put on Twitter the other day. I'm glad I can read your mind. 5% of people have had coronavirus. Let's say an antibody test has a false positive rate of 5% and a false negative rate of 15%. So 5% for false positive rate, false negative rate 15%. What is the probability you test, no, not you test, that's a given, hold on. You have coronavirus given that you test positive. Maybe it's not an antibody test. Maybe it's just our normal test. Um, so here's my problem I wanted to make up. This is my Bayes theorem problem. Okay, I've been thinking about this one over and over. I found out some new stuff. I didn't realize that test specificity and sensitivity are your false positive and false negative rates. It's on a tweet I put a while back. I did not realize that sensitivity and specificity are like the scientist terms for false positive and false negative rates. So every test you actually can look up what the false positive rate and the false negative rate if you knew the vocab. Um, so these numbers are about right. I heard that Abbott test that they had at the White House last week was about a 15%. No, it wasn't. They said it was a 15% false negative rate, but now they were saying that in some studies they had found a 40% false negative rate, which is crazy high. So I'm scared to even use that test now. But let's see. So we're going to do a tree diagram, and we're going to go through this. So tree diagrams are for these problems, right? These are tough problems without a tree diagram. So first thing, you either have coronavirus or you don't. So I'm just came up with what I think the percentage of people that have it. So you have virus or you don't. So 5% of people we're saying right now have the virus. 95% don't have the virus. Okay. And then, okay, if you have the virus, you take the test. You might get a positive or you might get a negative. So on this test, the chance of you getting a negative when you actually have it, that's your false negative. That is 15%. So we're going to put a 0.15 here. I should put those other ones in decimals. So let's change these to decimals. So 5% have the virus, about 95% don't have the virus. Okay. So there's a 15% false negative rate, and then that means that it would be right 85% of the time. It'll give you a positive, and it should have given you a positive. Now you don't have the virus, could get a positive, or we could get a negative. Now, if you get a positive test and you actually don't have it, that's your false positive. So this is the 5%. It's going to mess up and say that you have it, and it will be right 95% of the time. It'll say you don't have it. Okay, there's our tree. Remember, the trees I give you on these ones are just usually they're two-step trees, nothing too complicated. So we need to calculate. They ask you to calculate the probability that you have coronavirus given that you tested positive. So I first need, now if you go to your formula sheet, right, says that we do have and tested positive, and you divide it by the probability of testing positive, right? But I don't do the formula sheet because that complicates my life and I get lost. So I don't usually do the formula sheet. What I do is find, okay, since this is the given, we need to figure out what's the probability of just getting a positive test. So, probability of getting a positive test. This branch is a positive test, and this branch is a positive test, right? So, 0.05 times 0.85. So this branch, remember, you multiply down the branch, 0.05 times 0.85, and these positive tests, 0.0425. That's how many positive tests we're going to get out of there. And in the other group, 0.95% that don't have it, and we're going to have a false positive rate. 95% times 0.05. So 0.0475 is our percentage of people that get a positive test from that group. So our total positive test are those two added together. So the probability of just getting a plain old positive test are those two together. Wow, which is higher than I would have thought. So, wow, it's 0.09. Look at these beautiful numbers I made. So the probability of getting a positive test, just picking a random person off the street, is about a 9% chance that we get a person that has a positive test, just picking a random person out in society. Okay, now, what's the probability that you actually have coronavirus given that you got a positive? So, which one of these two branches actually had coronavirus? This one. So this is your group that actually had the coronavirus. So the probability of actually having it, given that you tested positive, is the branch that actually had the disease over the total percentage likelihood that you tested positive. So 0.0425 divided by the 0.09. So that ends up being the chance that you actually have coronavirus, given you tested positive, is only 0.4722. That should blow your mind a little bit. Absolutely blow your mind. That is your Bayes theorem problem. Okay, my mind is blown. I didn't make these numbers up. These are numbers that I have found as I've been researching coronavirus this whole time we've been out. I did not make these up. That LA County USC study found about 4.5% of people have had coronavirus. So that's probably about the prevalence right now in society. And those tests have been, I mean, there are definitely false positive rate and false negative rates on these tests. They're not perfect. Um, so look at that. That blows my mind, you guys. There's only a 50% chance. You got a positive test. You're this random person that went in and got a positive test. There's a 50% chance, 52% chance you don't even have it, right? There's a 47% chance that you have it. Wow, blows my mind. Blows my mind. You can tell how important that false negative rate is and that false positive rate. Those rates are so important. So it's crazy. It's crazy. But that's your Bayes theorem problem. Do I think you're going to get a Bayes theorem problem? I don't think so. I mean, I'm always afraid you will because they love these problems, but I just don't think so. The probability problems that I've seen so far on those practice videos I've given you guys on the practice exam, they have not been that they have not been that hard. The probability problems that they've given you have been very straightforward from your tables, like writing down the numbers straight out of a table. So I just don't think that they're going to give you um, that hard a probability problem. They could, but I just don't think it's going to happen. Um, but this was a good one. So I like this one. So if you guys, okay, tomorrow, 11 a.m., or make sure if you've taken AP test, you already know. Get on there at 10:30, logged in. You should check your email. You should have the AP exam ID emailed to you, ready to go for tomorrow. Make sure you have some paper ready to go if you're going to write them and take pictures of it. Make sure you have printed out your formula sheets that you need. Um, if you want to use the formula sheets, I probably wouldn't use the formula sheet. To me, complicates my life, makes me more lost. I might use this. I might use this. I don't need this. I don't need all this. You probably already know the basic probability formula. That was the one I wrote there, but we did with a tree diagram, so you didn't use it. The best assignments I've given you for doing review are the practice tests that they've given us. So I have given you 5 practice problems that they've given us over the last course of the last week. Those have been the best one. Because old FRQs are not guaranteed to look like they're going to have it. So if you felt good on those 5 problems, I think those are good. There is a there is an if you go to YouTube and type in AP statistics, the College Board put out all these review videos. Are some more videos on there. Practice problems. It's hard. It's hard to pick the right kind of practice problems for you guys. That's why I just wanted to pick the ones that they keep giving us. I'll look and see if there's any more on there. Um, but I don't think you necessarily need to do tons of practice problems. I think you need to be ready to answer why, what, that kind of stuff. I don't think doing more problems is necessarily going to help you. I think you watching the videos and knowing exactly like what you need to talk about, why you do stuff like that. This year's test is definitely more about why, because you're not doing as much. You're not as much like the assumptions that we check for our inference. You guys, I don't think you're going to have to check them. I think you're just going to have to say, why would you check it? Um, so those kind of things. I think it's more about concepts and like you have a good overall understanding. Um, So that's what I think. I don't think I think practice problems will just tie you up. I don't think it's helpful right now. I think the ones they gave you that I gave you last week, if you've done all those, you're good. You're good on practice problems. Try and think what else I have in here. Um, like the ones that I've gone over, right? No, not this one. I went over all of these last week. Oh, the terms I put in, that terms video, that one's a good one because that's a lot of whys. Why do we check for independence on inference problems? The reason we check for inference on independence on inference problems, the reason we do that would be the randomization condition and the less than 10% is because we can't use our formulas. The central limit theorem, right, says that our distribution is normal, but it's not normal if the independence is not met. So if independence is not met, then the probability changes as you go through the situation, and then you don't have a normal distribution. It's because of the central limit theorem. So in your book, if you guys want to review central limit theorem, chapter 18, that is the foundation of all the inference and why we do the different checks. Yeah, chapter 18 is your inference. So if you go to the blue page in the end of chapter 18, there's a little bit on there, but that's your central limit theorem is all about we use a normal distribution as long as all these conditions have been met. So that's why we look for independence between, that's why we have randomization in less than 10%. So the probability is not changing as you pick people to be in your sample. Um, it's all for that requirement. So I think the video I made for inference and we talked about the whys, that's important. Um, Trying to see what else. I gave you those. Yeah, I gave you these. Yeah, I just think the practice problems I gave last week, much more likely to have something like this. I don't think it's going to be, here, I'm going to be honest, you guys. I don't think you're going to have the hardest tests. I really don't. I think it's going to be straightforward. They've said they want to start A to be straightforward, easy, accessible to everyone. Um, so just understand, okay? It's not supposed to be kill you. It's supposed to be straightforward. Do you know everything? Do you know why you do everything? Not that you can do everything as much this year. It's more why are you doing everything? So send me a message if you have a question. You can send me a message on Remind. If you guys have a question tonight, send me a Remind message. Or you can send me a comment on Google Classroom and I can see it on there. But hopefully all goes well. As soon as everyone's done tomorrow, you can message me. We can talk about it. I can hear about what questions are on there. Unfortunately, I can't see it. Like I could see calc because my daughter was taking calc, so I got to see it. Um, so you guys are gonna have to tell me what you see. So I'll be interested to hear what we actually get. I know you'll do great. Um, you'll be fine. Just be confident. Listen to some good music between 10:30 and 11. Get yourself relaxed. My Twitter is at Mr. Shevlin. So just go to there if you want to send me. You can send me a message on Twitter. You can send me a message on Remind. You can send me a message on Google Classroom. Okay, I'm around today. Hopefully this video helped. It's long, I know. So here we go. We will see you guys. Good luck tomorrow. Wait, we should end it with some music. We should end with some music. Hold on. My YouTube did not let me put on music on my YouTube video, so I can only let it show up in here. But I'm going to search Brotherhood Dance Crew. We need some Brotherhood. Oh, what was this? Oh, that was a year ago. We already saw that one. That was 3 years ago. What's my classic? Oh, this one's pretty good. This one's pretty good. See you later. Jump rope by dancing. Sick. Sick. That was good. That was good. That was good. Okay, guys, we'll take it easy. That was nice. How to end our video on a good note.